Hi and welcome. Today we're going to talk about the chain rule. The chain rule is a really important rule in differential calculus as it allows you to take the derivative of what are called composite functions. What's a composite function? Well, let's say you have two functions, f and g, f of x and g of x. We can form a composite function, h, by taking one of the functions, let's say g, and putting it inside the other function. So g is going inside x, or f, and we will sometimes notate this f composed with g on x. Okay? So the chain rule says that if you have one of these composite functions h, then the derivative of h with respect to x can be written in terms of these pieces. And this is what it looks like. The first piece is the derivative of f, this one of these piece functions, derivative of f with respect to x, and we're going to evaluate that derivative function at g, and we'll talk a little bit more later about what that means. Then we multiply by, more straightforwardly, the derivative of this function g with respect to x. Okay, so this is one of the forms of the chain rule, and this is the form that we'll be using, and we'll unpack the meaning of these different pieces as we go through a couple of examples. All right, so let's get started. Example 1. Example 1. Let's start with two of these functions, f and g. So let's start with f of x is equal to 3x squared, and g of x is equal to 4 plus x. Okay, our first task is going to be to form that composite function. So what is that composite function? What is h if h is f of g of x? What is that thing? Let's find out. So f of x is a rule. F tells you how to take x, an input, and transform it. And here's the rule for doing so. We take this input x, we first square it, then we multiply by the number 3. So when I take f of g of x, I'm going to do exactly the same thing. I'm going to take this input, which is now g of x, I'm going to square it, and I'm going to multiply by 3. Okay, so I'm really just putting in g of x instead of x. I'm substituting in g of x for the input to this function. All right. Let's get rid of the g by substituting in the definition of g. And we find then we just have 3 times, and instead of g, I'm going to put in 4 plus x, because that's the definition of g, and that guy's going to all be squared. Okay. Let's use distribution to expand this thing. We'll get 3 times, and this is going to be 16 plus 8x plus x squared. And finally, what do we get? 48 plus 24x plus 3x squared. Okay, so I took these two component functions, I composed them, and I got this composite function here, h. Now, let's find out what the derivative of this thing is. And I don't need to use the chain rule in order to do this. I can just compute the derivative because I have some sums of powers. And so I can use the power rule and compute this thing straight away. So here we go, dh dx is equal to derivative of a constant is 0 plus 24 plus, and then bringing down the 2 times 3 is 6x. So I get 24 plus 6x. Okay, easy enough. Now let's use the chain rule to compute this very same thing. Okay, let's remind ourselves what the chain rule is. It says dh dx, the derivative of the outside thing, or the derivative of the composite thing, rather, is equal to the derivative of the outside function f. Here f is the outside function, g is the inside function. It's the derivative of the outside function evaluated at the inside function times, and then the derivative of the inside function. Okay, So in order to compute this thing, I need a few pieces. I know what g is already, g is here, but I don't know what df dx and dg dx are, so let's compute those. All right, df dx then is equal to, and this is a simple power rule, which just gives me 6x. dg dx, this is even simpler, is equal to just 1. Okay. Let's plug this stuff in. So dh dx is equal to, now df dx applied at g of x. What does that mean? Well, df dx is itself a function. I can notate it this way, maybe f prime of x. So it's some function that takes in an input x and it spits something out. And in particular, it spits out 6 times the argument. So this function here, df dx, applied at g of x, is going to take in this argument, g of x, and spit out 6 times the input, or in other words, 6 times the argument g of x. And then we multiply that by dg dx, which is equal to 1. So fairly straightforward. All right, so we've done the hard part, and now we just have to substitute in what is g. G is given here by its original definition, 4 plus x. So dh dx is equal to 6 times, and then g is 4 plus x. Okay, and then the moment of truth, let's hope we get this right. dh dx is 6 times 4 is 24 plus 6x. And lo and behold, using the chain rule, we got the same thing as if we just expanded the whole thing out and computed term by term. Okay, so the chain rule works. Great. Why, though, should you bother to use this new technology, this new technique, instead of just doing this, which seems straightforward enough? Here's an example which should convince you that the chain rule, or it's one reason that the chain rule is important to know. So let's take our previous example and let's modify it just slightly. Example 2. Let's say that f of x now is going to be equal to 3x to the 100. Okay, so we're going to bump up that exponent. And g of x, the inside function, let's let that be 4 plus, and last time I had 4 plus x, let's make it 4 plus 2x. Okay, so those are my two component functions. Let's combine these and form the composite function h of x, which is by definition, I guess, f of g of x. Okay, so again, f is a rule, takes an input x and it outputs that input to the 100th power times 3. So if I use that rule, but I apply it to g of x, then I get my input to the 100, my input to the 100 times 3. And maybe I'll put parentheses around this g of x just to remind us that this power of 100 is being applied to the whole of g of x. Okay, now let's plug in for g of x. What is g of x? G of x is 4 plus 2x, so we get 4 plus 2x to the 100. Okay, now at this point, what we did last time, if you remember, at this point, after we plugged in for g, we expanded this guy, and then we did term-by-term derivatives in order to compute the total derivative, or the derivative of the composite function. I could, if I had a lot more time and patience, write out this whole thing. And what's that going to have? Since it's a 100th power, it's going to have 101 terms in it. Okay, that's going to fill up more than just this paper, and I don't want to do that. So I know how to do this, but I'm not going to do it because it's too much of a pain. So instead, I'm going to make use of this new technology, this chain rule, to do the heavy lifting for me. So let's remind ourselves again, because it's always worth it. The chain rule says that the derivative of the composite function with respect to x is equal to the derivative of the outer function, df dx, applied to, or applied at, g of x times dg dx. Okay? And once again, I need to know what are these two derivatives, df dx and dg dx. Let's compute those. F